Thank you. Hi, everyone. I'm Vaibhav, and today I'm going to talk about Hoare logic for symmetry properties. So first up, what is a symmetry property, and why should you care about that? Well, to answer that question, I'm going to go through a series of motivating examples. So first, let's consider a voting system where you have two candidates, a cow and a duck. And suppose you have three voters, and they come in and they cast their vote one by one. And suppose we declare the cow is the winner of this election, and you use some method to decide this, doesn't really matter. And now you want to verify some correctness property. There's many correctness properties for such a voting system you might want to verify. But one property you might care about is anonymity, which is to say that the identity of the voters should not matter, right? And the way this is typically formalized is we say for any permutation of the input or for any permutation of the voters, the output or the winner of the election, which is the cow, remains unchanged. So in this example, we're interested in a family of transformations on the input, which is all the permutations, and the effect that they have on the output, which is invariance. But in other settings, there's other transformations we might care about. For example, suppose we wanted to verify a cyber-physical system. Specifically, imagine you have a car that's trying to reach some destination or waypoint, and it's just traveling in a straight line. And now you want to prove some safety property about this system. Now, in general, this can get quite complicated. So one trick researchers do to simplify their reasoning is that without loss of generality, they assume that the destination of the waypoint is at the origin or at 0, 0. Now, this is useful because knowing that this is 0 lets you simplify any program expression verification condition which mentions this. But another interesting question is, why is this sound and when is this sound? Well, in this case, it's sound because this program preserves translations on the input. Meaning, if I translate the car by some amount, the starting position of the car by some amount, and I run the program, or the car moves in a straight line, the final position preserves this translation. So translating the car's position by some amount leads to the same translation on the output. And this could be any translation. So here again, there's a family of transformations, which is all the possible translations on the input, and the effect that they have on the output. So we see that this notion is useful as a correctness property, and it's also useful as a way to simplify proofs. And our goal with this work is to formalize and verify such properties. And to that end, we have two major contributions. The first is a program logic for verifying these symmetry properties. For this, we develop a novel assertion language using ideas from group theory, which I'll explain in the next few slides. And then we develop some Hoare-style proof rules for reasoning about these assertions. And then we have a prototype implementation, which we use to automatically verify such properties on real examples from across the literature. So in this talk, I'm going to focus mostly on the first contribution, which is the program logic. And to do this, I'm going to give you some group theory background, but I promise it's not that bad. So a group is a set G, which is endowed with some binary operation, which we call group multiplication. And we have some axioms that this operation is subject to. The first is we demand that this operation be associative. The second is the identity axiom, which says there should exist some element E in the group, such that this element E multiplied with any element just gives you the element itself. So this element does nothing. And the third is every element should have an inverse. So for any element A, there's an element A inverse such that if I multiply the two, I get the identity. So an example of this that maybe we're all familiar with is the group of integers. Under addition, they form a group because, well, addition is associative. 0 is the identity because a number plus 0 is just the number itself. And the negative of a number is its inverse because a number plus the negative is just 0. So groups are great. But what we really care about is the transformations that they induce, specifically the transformations they induce on program states. And this is captured by a notion called a group action. So a group action is of a group G on the set of program states is a map or a function A that takes in a group element, a program state, and it spits out a new transformed program state. And we require this map to satisfy some axioms, but for this talk, those axioms aren't really important. So if we take the group of integers, let's think about how it might transform program states. Well, it might transform a program state by adding integers to the variables x and y. And so we'll denote that as follows. We'll write the name of the group, which is the integers, the name of the action, which I'm going to call add for addition. And I'm going to say that it's going to modify the variables x and y. And the way it's going to do this is it's going to take in an integer n, take in the variables x and y, and add n to the values of x and y. So in our paper, we define a flexible and compositional syntax for defining these group actions. So they're not actually built in like you see here, but rather you're free to define your own transformations. And these will serve as assertions in the logic. So now that we have the assertions, we can move on to actually defining the logic and seeing what it looks like. So this is what the triples in our logic look like. And the key difference from our logic and Hoare logic is that the pre and post conditions are now group actions. So we have a precondition group action G, GA, which acts on the input. And we have the program, and then you have a post-condition group action HB that acts on the output. And intuitively, a triple is valid if for any transformation on the input by GA, there exists a transformation on the output by this group action HB. Or in pictures, this is what it looks like. If I start with some program state sigma 1, apply any transformation from the group action GA to obtain sigma 2, and then I run the program C. If this is the same as just running the program C and relating the output, and I can relate the output of running the program C via the group action HB, then this triple is valid. And so this is roughly what validity in our logic looks like. And so for the rest of this talk, I'm going to explain how you can use our logic in what I think is a fairly intuitive way to verify symmetry properties. And to do this, we're going to verify a small toy program. Specifically, we're going to consider this simple program which models a car moving in a straight line. So we have a for loop here that runs for capital T time steps, and the loop counter variable small t is incremented by some small constant dt, which represents the time passed per iteration. And so in the loop body, for every iteration, we update the positions of the coordinates of the car, x and y. And the way we do this is we take the velocity along the x-axis, multiplied by dt to get the amount we've moved along the x-axis. And then we add this to the old position of x to get the updated position of the car along the x-axis. And we do the same thing for the variable y. And so if you just keep running this loop, you get a car moving in a straight line as the x and y coordinates modify. And we want to show that this car moving in a straight line preserves translation, meaning if I add any integer to the variables x and y when I start this program, and then I run this program, at the end, the positions of x and y will still remain shifted by by any integer that I started with. And so, how do we prove this? We'll use rules from the logic, of course. And to start with, I don't like the for loop, so we're going to try to get rid of this. And how are we going to do it? Well, our logic has a for loop rule, or we also have a while loop rule, but here's a stylized version of our for loop rule, which says that if a command C preserves the group action, meaning it has the same pre and post condition, then running it for t time steps will continue to preserve this group action. And this notion of preserving a group action here is our analog of a loop invariant, essentially. So now our only proof obligation is to prove the stuff above the line, which is we need to prove our loop body actually preserves the group action we care about. And so how are we going to do this? Well, this is our loop body, and we're going to apply rules from the logic to try and fill in all these blanks. So let's start with the precondition that we care about, which is the addition group action. And now we have an assignment statement, right? And so we should apply the assignment rule from our logic. And indeed, we do have an assignment rule in our logic. I'm not going to spell out the details of what of how this assignment rule works, but I hope you'll believe me that it gives us some intermediate group action, which I'm going to call B, which is still a group. It's still the action of the group of integers, but it's maybe doing something different to the program state, and it's still modifying the variables x and y. And so now I have this intermediate assertion B, and I'd like to be able to string through a sequence of judgments and talk about the post condition of y. But to justify this sort of thing, I need a sequencing rule. And so similar to regular Hoare logic, our logic also has this. And the sequencing rule says if a command C1 has the same post condition, if this command C1 has a post condition that is same as the precondition of some command C2, well, I can just sequence them together and get a larger judgment. And so now if we go back to our program, I can start with this group action ZB as my precondition for y, apply assignment, and now I get this new group action that's somewhat mysterious, which is this group action I'm going to call C. And then by sequencing, I can justify this big judgment, which says, okay, that the loop body, if I start with the group action add, I get some group post-condition C. And maybe this is a bit troubling, right? Because we want add in the post-condition. So what do we do now? Well, in standard Hoare logic, you check to see if there's some entailment or implication thing you could do. And our logic also has a notion of entailment. So a group action GA implies another group action HB if the group action on the right, HB, contains all the transformations in GA. So essentially, if HB is a bigger group action than GA, we can say GA implies HB. And so using this notion of entailment, in our logic, we define a weakening rule, where if you've proven some triple GA C HB, you can prove that HB implies some other group action IC. You can always weaken your judgment to say that I is the post condition. And so it will turn out in our setting that this group action C that I have not defined actually implies the addition group action that we care about. And so if we use weakening, we can essentially prove what we wanted, which is that the loop body preserves the addition group action. And so putting it all together, this is what we've shown. If you add some integer x and y, some integer to the starting positions x and y, and you run this program where the car moves in a straight line, you will end up in a situation where the final position of the car is translated by the same amount. And so this is what a lot of the proofs in our logic look like. They're very similar to Hoare-style proofs. And so just wrapping up, in this talk, I presented a novel program logic for reasoning about symmetry properties. The key insight was we use group actions as a way to formalize assertions, allowing us to express many transformations in one go. There's lots more in the paper. There's lots of structural rules that take advantage of group theoretic structure. Groups have a lot of mathematical structure where they're able to exploit to have some interesting structural rules using group products. We define weakest precondition in our setting, and we show under certain conditions it exists, under certain conditions it doesn't. And based on our weakest precondition, we actually implement all of this in a tool which we use to automatically verify many symmetry properties. And of course, our artifact is available, et cetera, and all that. And I'm happy to take any questions. Thank you.
If you could introduce yourself before your question.
Jules, undergrad in NUS. I think it was very interesting. One question, I think that it might be quite common whereby like a part of the program doesn't preserve a group action, but another part of the program reintroduces a group action. So like how does this get handled in your system?
I see. So when you say, I guess, sorry, there's two issues here. One is, it's in our system, it's fine if it doesn't preserve the same group action. So our rules may not always give you the same group action. So you can start with some group action, and you could end up with some different group action as an intermediate assertion. And then maybe at the end, you'll end up with the group action that you want if the property holds. There is this other issue of sometimes there may not actually exist a valid group action in the forward direction, which is why often we have to do backward reasoning in our system, which is where the weakest precondition comes in. Because in the backward direction, there always exists at least the identity, the trivial group action. So that way, we're able to kind of avoid this sort of issue. But that's a good question. Thank you. Yeah, thanks.